Hey guys, this is attempt number 2 at this video. I kind of started with a bunch of bad mistakes, so I'm starting over. Hey, let's take a quick review of what we know so far. We've seen 3 what I'll call examples of series, although they're like infinitely many examples actually, because 2 of these are infinite classes of series. We've seen geometric series. It's a constant multiple of r to the n. I'm going to ignore the constant multiple for now so I don't have to think about, there's these asterisks about if that constant is 0. Let's forget that for a second. A geometric thing will converge when the rate, its growth rate or decay rate, r, is between -1 and 1. I'm putting the -1 part in parentheses because mostly we care about positive series for now. We will care more about negative series later, but we did check at the time that if r is negative, as long as it's not bigger than -1, it does converge, and when r is outside that interval, it diverges, and it converges to the first term over 1 minus r. And we're probably expected to have that formula memorized. Right. We talked about p-series. A p-series is the series 1 over n to the p. It converges if p is bigger than 1. It diverges otherwise. If p equals 1, it diverges. If p is less than 1, it diverges. Mostly we're talking about positive p values, but it also diverges for negative p values, or if p is 0. And we have the harmonic series. This is only one series and it diverges. This could be called one of the p-series, but you sound dumb if you call it a p-series, because it's got its own fancy name. And now we have tests. So those are specific series that we're allowed to say, hey, I know this converges, I know this diverges. They are things that we just know. We're going to end up with 7 tests. I'm going to leave this page up so that I can put the shorthand versions of all those tests in here as we fill them in. We have the divergence test, which is like a bare minimum for something to pass. It says that if the terms don't converge to 0, if the limit is not 0, there's 2 ways it cannot be 0. It can either be a number that is not 0, or it can just not exist. In either of those cases, the series diverges. We have the integral test, which is turn the series, like think about the function that generates the series in order to understand the series. The integral test says if a function is positive and decreasing, then the corresponding series converges if and only if the integral of the function converges at infinity. And from somewhere to the function, depending on if the function is always positive and decreasing. If it only starts being positive and decreasing after n equals 20, then you should probably think about the integral from 20 to infinity. Because maybe the function diverges for other goofy reasons before 20 that we don't care about. All right, next up we're going to talk about direct comparison and limit comparison. The idea here is if I can look at a series and understand it's about the same size as this other series, and I know that other series converges or diverges, hopefully because it's a p-series or geometric series or something else that I'm able to understand by some way, then that should tell me something about this series. Let's take an example. Let's consider the sum from n equals 1 to infinity of 3 over 2 to the n plus 1. How big is this? 3 is about as big as 3, which is basically about as big as 1. It's a constant. Any constant is the same size as far as convergence or divergence matters. I could factor that 3 out if I wanted to. I probably don't need to. I could. How big is 2 to the n plus 1? Well, 2 to the n is very big, and 1 is not very big at all. The 1 basically doesn't matter. 2 to the n plus 1, I want to look at that and think it's about the same size as 2 to the n. In particular, like a more detailed version of that is that 2 to the n plus 1 is strictly bigger than 2 to the n. It is basically the same size, but in particular, it is a little bigger. The fact that it's bigger is mostly irrelevant, because it is only a tiny amount bigger, but it is bigger. What do I know about fractions? If 2 to the n plus 1 is bigger than 2 to the n, which it is, what does that tell me about 3 over 2 to the n plus 1 versus 3 over 2 to the n? There's a good chance you haven't done this type of little in-your-head heuristic before, but hey, if you make the top bigger of a fraction, you've made the fraction bigger. And if you make the bottom smaller, you have made the fraction... Damn it, I wrote that the wrong direction. If you make the top of a fraction bigger, you are making the fraction bigger. If you make the bottom of a fraction smaller, you are making the fraction bigger. This is assuming that a and b are both positive. If things are negative, everything gets weird. Just thinking about the positive case. Making the top bigger makes the fraction bigger. Making the bottom smaller makes the fraction bigger. This is a thing that you can keep in your head. It's not a... In the course of writing these things out, that's not a step that you need to verify. You're allowed to just look at this and say, hey, smaller bottom is a bigger fraction. This is clear to see if you understand this heuristic. You're allowed to assume that the person reading you understands that. Like, you're writing to a mathematical audience who understands at least this much. This is a really hard thing to do in math writing, is knowing how much you need to explain. Does my audience definitely know this? This is a step you don't need to explain. You're allowed to just know this. So this term is bigger than this term. I want to be able to conclude from that, so a sum of 3 to the n over 2 to the n plus 1 should be smaller than a sum of 3, not 3 to the n, just 3, over 2 to the n plus 1. The thing I'd really like to say is that this is true for the infinite sum. And that will turn out to be true, but at least once I should go through the details of doing this the correct way. The reason I would care about that is... You're not here. The sum of 3 over 2 to the n exists. That is a constant. I could actually tell you what the constant was if we needed it. We don't particularly need it. And it's a finite number. It's not infinite. And if this infinite sum is smaller than a finite number, it must be finite. The answer would be that it converges. Maybe I should write the question out. Question. Does it converge? It's our main question that we're asking about series right now. Just like for exam 1, our question was, do this integral. Now our question is, here's a series, does it converge? Explain why. Explain why with complete sentences. And this is true, that this thing is less than this thing, which is finite, therefore this thing is finite. We're going to start using definition. Infinity is not a real number, but we put it in the order. Meaning a is less than infinity for all a. It means the thing that you think it means. But heads up, there's a good chance you've never actually written 5 less than infinity in a way that was defined. Like, you need to... You're not talking about real numbers now, so you need to explicitly say, hey, infinity isn't a thing you're allowed to add or subtract or multiply, but it's bigger than every real number. I am allowed to write less than infinity, and that means something. And in particular, infinity is not less than infinity. When I say you are less than L, yeah, you're less than a finite thing, you're not infinite, yeah. And I guess part of that reasoning is all these terms are positive. There's no chance of anything going to negative infinity. Either it's finite or it's positive infinity are the only options for when you're adding up positive numbers. Okay, so I want to be able to say that, but at least once I should go through and do it in the precise way. I don't get that immediately. I know that step 1 is that the term is less than the term. I should write that out first. That's the thing I'm allowed to say for free. From that, I conclude that the sum from n equals 1 to big N, I guess normally we've been writing this, the sum from k equals 1 to little n, of 3 over 2 to the n plus 1 is less than the sum from k equals 1 to n of 3 over 2 to the n. Therefore, oh, it's not, these are supposed to be k's. The thing on the right has a limit. The sum from k equals 1 to n over of 3 over k, 3 to the k plus 1 is less than the limit. If you're less than this for all numbers, like if you're less than every term of a sequence, then you must be less than the limit of the sequence, if the limit exists. And this limit does exist. I can tell you what it is. It's a geometric series. I don't actually care what it is. I know that that series converges. That means the limit of the partial sums converges. That's the definition of what it means for a series to converge. We're proving that this is true, you going all the way down to the definitions. This limit exists. So, Sn is the sum from k equals 1 to n of 3 over 3 to the k plus 1 is bounded above. I know it's bounded above because I just said it's less than this number L. And it's increasing. Why is it increasing? Well, every term, the term after it is the last term plus 3 over 2 to the k plus 1. So Sn minus 1 equals 3 over 2 to the k plus 1. 3 over 2 to the n plus 1 is positive. The sequence of partial terms is bounded above and it's increasing, so it has a limit. So the series converges. A sequence of partial sums, or a series converges exactly when the sequence of partial sums has a limit, and this we just said the sequence of partial sums has a limit, so the series converges. We don't want to write that out every time. This is me going through the details of one example of the direct comparison test. Let's write out the direct comparison test, and then let's use that to be the slick way we write out our answer to the question, does it converge? The thing we've just done is way more detailed than you really want to be doing in a general version. If I wrote this out for a general sequence AK and BK, the thing we could conclude, the direct comparison test, suppose AN and BN are positive sequences. Do they have to be positive? Well, I used that they were positive here. That's what made it an increasing bounded sequence, is part of the requirements for being, for that theorem we used. That axiom we used. It's not even a theorem. And it's easy to, if you draw the picture, to say that, yes, they do have to be positive. It's not going to work if they're not. Suppose you have two positive sequences. If AN is less than BN, or if it's just less than it eventually, let's write this out assuming that AN is the sequence I want to know about, and BN is the sequence I do know about. A is the thing they gave me, is why I'm putting it first alphabetically. B is the thing that I'm bringing to the table that I can say I know. Then, if BN converges, then AN can. If the sum of BN converges, then the sum of AN converges. If the sum of BN is finite, and an is less than it, then the sum of an is finite. If you're less than finite, you must be finite. If an is bigger than bn, or if it's just bigger than it eventually, then if the sum n equals 1 to infinity of bn diverges, then the sum of an diverges also. If you're smaller than finite, you're finite. If you're bigger than infinite, you must be infinite. And yeah, you can see if these have to all be positive for this to make sense. This is direct comparison. That's the thing we were using just then. How would I write out a usage of the direct comparison test? Part of what you want to be clear about is, like, you can see immediately why I was warning you last time about be careful about saying things like it converges. If I'm using this, then I'm talking about one sequence, two sequences, plus one series, plus another series. If you're saying it converges, that's at least four things you could be talking about at the end of the paragraph. Like, once you've talked about all those things, they are all floating around in the ether and could be the it you say in a sentence. Does it converge? We have that 3 over 2 to the n plus 1 is less than 3 over 2 to the n, and I'll say bigger than 0. That means both of those things are 0. One of my conditions is that I need the things to be positive. I'm mentioning in my explanation that they are positive. And I'm also at the same time saying that this term is less than this term. Since the sum from n equals 1 to infinity of 3 over 2 to the n converges. Why do I know it converges? It is geometric with r value of 1/2, and 1/2 is less than 1. Notice how I've sort of got a lot of detail packed into this parenthesis. I'm really cramming it in. A geometric series converges when its r value is less than 1. So I want to say, why does this converge? It's geometric, and a geometric series converges when its r value is less than 1. Maybe this part is not required. I think you could make a case that you should understand what I mean. I said it converges because it's geometric, and I didn't show you what the r value is. If I was writing this to another mathematician, I wouldn't explain that, because they know what a geometric series is and when it converges. Right now, you're kind of being tested on your ability to explain why you know a geometric series converges, so I think in your context it makes sense to add a little bit more detail. But, like, this is the thing that you are explaining that you know. Like, this is the very content of this course, so you're adding a little bit more detail than necessary. So I would do that, but I probably also wouldn't take points off if you didn't put that. I guess I reserve the right to change my mind when I'm grading, though. I don't think you need it here. Maybe there are other cases where you do need it. Since that series converges, and it converges, I know it converges because it's geometric and its r value is less than 1. And, geez, I guess I should... It's not just less than 1, it's bigger than negative 1. Should I add that? I'll just say r value equals 1/2. That way I don't have to deal with the absolute value thing. If I was adding that more detail, and absolute value of r is less than 1, that's not a question. I'm thinking a question mark about, does it sound good to write it that way? I'm sorry, it probably sounds like I'm thinking really hard about crafting the perfect sentence, and that's not usually a thing you need to be doing in the homework. I'm trying to think about this because this is like my prototypical example sentence, and I really want to make sure I'm phrasing. This is the most detail. You can probably cut this and be okay. You can maybe cut all of this and be okay. Anyway, it's since this series converges, we have the given series converges as well by direct comparison. And that's all we need to say. The words direct comparison are doing all of this mess for us. This is why we prove theorems, so that we can cite them later. Right. Here's a pretty good example paragraph using direct comparison. Often, eventually we'll see one where we're talking about divergence. I guess we'll get to that example eventually, but you can imagine how it goes. Change the 2 to a 1/2 and rewrite all of that the other way around. The thing I want to get to is limit comparison, and then when we have the problems all mixed up, we'll see different versions of everything. Let's consider 3 over 2 to the n minus 1. And again, the question we want to ask is, does this series converge or diverge? How big is 3 over 2 to the n minus 1? Well, I understand the series 3 over 2 to the n. It's geometric, and I know it converges. I guess I'm hoping to know that you're smaller than finite. If you're smaller than finite, then I can do it. Are you actually smaller than finite? Oh no, you are a bigger fraction. You have a smaller denominator. That makes a bigger fraction, so it's this direction instead. Dang it. I can't use direct comparison. Well, that seems unfair because the minus 1 isn't actually doing anything. The smarter way to look at it is that 2 to the n minus 1 isn't really smaller than 2 to the n. It is literally less than it, so yes. But in the broader sense, they are basically the exact same size. What do I mean by they are the exact same size? I mean the ratio of them goes to 1. And I feel like this smarter idea, thinking about the ratio instead of the difference, should have some value, and it does. The value is in limit comparison. I want to think about what's the ratio of 3 over 2 to the n minus 1 with 3 over 2 to the n, and I guess I'm going to write it the other way around, because you like to put the known function on. What do you do? Let me look at the order that I wrote it in. I'm going to put the known function on bottom. 3 over 2 to the n on bottom, 3 over 2 to the n minus 1 on top. You can make the statement either way. I'm going to express the statement in a way that you'll be able to understand it in either direction. But this is the way it's formally written. When I say that 3 over 2 to the n is about the same size as 3 over 2 to the n minus 1, what I'm really saying is that their ratio is about 1. What is this limit as n goes to infinity? The 3's cancel. I get 2 to the n over 2 to the n minus 1. This limit, if I do the trick where you multiply the top and bottom by the largest function on bottom, is the limit of 1 over 1 minus 1 over 2 to the n is 1. It's 1 over 1 minus 0, which is 1. So, the fact that the limit is 1 says that the ratio it's not always going to equal 1, but it's eventually going to be so close to 1 that it's, say, less than 2 and bigger than 1/2. Eventually. That's like part of what it means to be a limit, is eventually you will be close to 1. You'll be within epsilon of 1 for any epsilon. If I use epsilon as a half, then this will be true eventually. So we have 3 over 2 to the n minus 1 is less than a constant multiple of 3 over 2 to the n, and it's bigger than a constant multiple of 3 over 2 to the n. Well, I know a constant multiple of 3 over 2 to the n converges if and only if the original converges. That constant multiple isn't doing anything. So I've got 3 over 2 to the n minus 1 is bigger than something that maybe converges or diverges, and it's less than something that maybe converges or diverges. Which means, since I have it both directions, if that other function converges, I'm less than it, so I must converge. If that other function diverges, I'm also bigger than it, so I must diverge also. If I know the direct comparison test, which I do, this will work in either direction, which makes the limit comparison test great. The key thing going on here is that the limit was 1, is a constant number. And it could have been any number as long as it wasn't 0 and it wasn't infinity. If the limit is 0, I can still say something. Actually, let's state the main version. I think most calculus textbooks only write this first version of the limit comparison test. And it's the version that's small enough to fit in the box I put up there a second ago. But it's easy enough to keep in your head what happens if the limit is infinity, what happens if the limit is 0. Is it important that the terms are positive? I guess when I use direct comparison here, I need these terms to be positive. So yeah, I need an and bn to both be positive. If an and bn are positive series, and if the limit as n goes to infinity, I think we write it as an over bn. Yeah, I want to think of it as the known function on bottom, because fractions with simple denominators are usually easier to manage. So if this limit is L, where L is not 0 and L is not infinity, it couldn't be negative infinity because these are positive series, so the ratio is positive. You can't go to negative infinity if you're positive. Then, the sum of an converges if and only if the sum of bn converges. Which immediately gives the sum of an diverges if and only if the sum of bn diverges. We're not going to write that out. If and only if means if one is true, the other must be true. So if one converges, the other converges, which immediately also means if one is false, the other is false. So if one of these diverges, the other one diverges. This is how many calculus textbooks write the limit comparison test. They demand that the limit not be 0 and not be infinite. But it's easy enough to draw a conclusion if the limit is 0. Because if the limit of a fraction is 0, that says the top is eventually smaller than the bottom, right? And I know how direct comparison works that way. If bn is my known function, I know now that an is eventually less than bn. Direct comparison works. So I get at least one direction if bn converges. Then an converges. And if the limit is infinity of an over bn, let me put my colon here. It's pretty bad writing to say then if. I did it on the last statement too. What's the classier way of writing that? Putting a big colon helps. I guess here's the nicer way to write that. If an is less than bn, and if bn converges. Yeah, if both of these things are true. Don't write if this, then if this. That gets bad if you have to do it more than twice. Oh, yeah. I just did the and. If the limit is infinity, and if bn diverges. If the limit is infinity, then the top is bigger than the bottom. So if I know the sum of the bottom, I forgot the sigmas. If the sum of Bn converges, then the sum of An converges, is the point. Then the sum of An diverges. I'm talking about the sum, not the... This is the mistake I just said. You need to keep in mind. Don't talk about the sequence when you mean the series. Don't talk about the series when you mean the sequence. When I say these sentences, pay attention to, are we talking about the sequence or the series here? Are we talking about the sequence of terms or the sequence of partial terms when we talk about the sequence? There's two sequences. Okay, this is the limit comparison test. This is sort of a little add-on to the limit comparison test. Most textbooks will just give you this one and not mention the other thing. I say you're welcome to use this other thing and call that the limit comparison test. Keep in mind your next calculus teacher might not agree, although you don't really talk about the limit comparison test after Cal 2 again. I mean, you use it, but yeah, anyway. Oh, okay. I have it written down wrong in my notes. I'm confusing myself. So let's try using the limit comparison test to answer this question. I worked out the limit over here. Let's assume that I did that on scratch paper, and now I want to try and write out my answer. Hey, heads up, on the next exam, you're welcome to use as much scratch paper as you want, but I'm going to ask that you turn in a thing. So I'm going to ask you to turn in the scratch paper. Like, give me pictures of that also. Like, I want, if you're doing this limit, just show me what your scratch was. That makes it easier. Consider this series. Let's see, what do I need to conclude for the limit comparison test? I need to know that they are positive. And I'm comparing it with 3 over 2 to the n. I could compare it with 1 over 2 to the n, actually is even easier. It'll change the limit from being 1 to being 1/3 or whatever. I want to write out the computation of the limit. Since I've done, maybe this took me a million steps to do because I take little baby steps. I would like to write out a slick version that is only writing out the max, that is only writing out what's necessary. Since 3 over 2 to the n minus 1 and 3 over 2 to the n are both positive series, are both positive sequences. And the limit as n goes to infinity of 3 over 2 to the n minus 1 over 3 over 2 to the n is the limit as n goes to infinity. 2 to the n over 2 to the n minus 1. Multiply the top and bottom by 1 over 2 to the n. Looks like I can probably skip the next line. Is 1 over 1 minus 0 is 1. So anybody, like, your goal isn't necessarily to show absolutely every step in mathematical writing, but your goal is to make it clear enough that if it wasn't obvious at all, anybody who's reading this and is smart enough to be reading mathematics can foil this out and conclude, yeah, okay, I see what you're doing there. The steps that you are indicating are clear, even if you're not writing out all the detail yourself. You're writing it clearly enough that anybody who, I guess, has taken Cal 2, can follow what's going on. All right, since this limit is 1, so since they are positive and this limit is 1, I want to say we can make the conclusion, but I need to also fold in the fact that I know 3 over 2 to the n converges. I don't want to fold in another and since, because that's going to muddy the waters. So I'm going to say we have, I'm going to break it into 2 sentences. We have that these sequences are positive, and the limit is 1. Since the sum of 3 over 2 to the n is a convergent geometric series, one half is less than 1. Hey, look at this, a little tiny shorthand to show that I understand what's going on with the r value. The r value is 1/2, and 1/2 is less than 1. I was able to compress what felt awkward in the last one, writing out with r, it's geometric with r equals 1/2 and the absolute value of r is less than 1. I got geometric outside of the parenthetical, which made this a lot cleaner. It's a convergent geometric series, because 1/2 is less than 1. Should I say because 1/2 is less than 1? Nah, that's enough. We'll do the bare minimum here. Since this sum is a convergent geometric series, I guess I'll be good and write n equals 1 to infinity, although I think if you skip that eventually, it's probably okay in some circumstances. Since this sum is a convergent geometric series, the given series is convergent as well by limit comparison. You could say by the limit comparison test. This is the fewer words. Like, this is clear. I guess this is like a turn of phrase that you're allowed to use. You could say by. I guess I wouldn't say by ratio if it was by the ratio test. Yeah, we have that both sequences are positive and the limit is 1. Since this series is a convergent geometric series, the given series is convergent as well. Oh, I forgot the word well, as well, by limit comparison. A thing you want to avoid is you want to avoid saying, since this is a convergent geometric series, comma, if I start writing math again, like I'm writing this math, comma, that math, it's a little bit difficult to read sentences that have, like, noun phrase, like there are times that you write, because the dog was wet, comma, I went to the park. You can put the independent clause, the dog was wet, right before the noun I. I'm actually writing this out. Wait, why am I going to the park because the dog was wet? What would I do because the dog was wet? Because the dog was wet, it smelled. If I'm writing math, there's a chance that the dog was wet, I guess with the, this might be a math expression. Something like that. And it might also be a math expression. And writing because math junk, comma, math junk, it's really easy for that comma to get lost there. You want to try to avoid writing two different mathematical expressions consecutively in the same sentence. That's hard to read. It's not like grammatically wrong or anything. It's just hard to read. And you want to avoid it if you can. So it's nice having little noun phrases that you can use to indicate math without writing math right then. And here I'm using the phrase, the given series. What do I mean by the given series? I mean the one you gave me in the problem. That's what the word given is doing here. This isn't a math word, this is an English word. The series you gave me is also convergent. And I'm doing this partly because I don't want that consecutive with this other math expression. Okay, I'm getting real down into the sentence construction conversation here. This is really the hard part to get into, and it's really hard for me to get myself talking about English. I feel like I'm doing great. I'm nailing this lecture, you guys. This coffee's delicious. Damn it, I keep not muting. I mean to mute when I take a sip, but I'm not smart enough for that yet. Sorry if that's gross in your ears. I know I hate it. If I'm listening, especially in headphones, it's gross to have someone's swallowing sounds right in your ear. Sorry about that. Let's do an example. These comparison tests are great. They make us pretty good at understanding sequences in terms of simpler sequences. If I consider the sum from n equals 1 to infinity of 2n squared plus 3n over the square root of 5 plus n cubed. What would I want to do here? Well, the last thing I talked about was limit comparison. There's a good chance we're going to do limit comparison. When you're doing these comparison tests, the big question you have is, what are you going to compare it with? And to do that, you want to understand about how big is this sequence. How big is the top? I have an n squared, I have a 3n. If n is a million, then n squared is a million. What is that, a trillion? This is 2 trillion plus 3 million. 3 million is nothing compared to 2 trillion. The important part for big N values is whichever part of the top is biggest. This thing is about as big as n squared. How big is the bottom? Well, it's the square root of something, but that 5 plus n cubed is n cubed. This one's not approximate, this is equals. What is n squared over n cubed over square root n cubed equal? These are all powers of n. That's about n squared over n to the 1.5. That's n to the 1.5. N to the 0.5. That's the square root of n. According to my estimations, this fraction should be about as big as the square root of n. Maybe give or take a constant. Does the sum of square root n converge? What do you do? That diverges. How do I know it diverges? I guess it's a p-series with p is negative 1/2, but I feel like a dope if I phrase it that way. We don't really use p-series with negatives because it diverges for the much more obvious reason that the square root of n goes to infinity, and infinity is not 0. It diverges by the divergence test. I'm welcome to use the p-series version, but I sort of feel like I'm proving that I understand what's going on a little bit better if I use the divergence test. I can't think of a good analogy, but you want to, if there's a very obvious reason that something is true, then you look kind of silly using a very particular reason that it's not true. Like if I was trying to convince you that, what would I be trying to convince you of that's not a math problem? It's not coming to me. If I was trying to convince you of if I was trying to convince you the sky is blue by going through and using the chemistry equations that are whatever causes the sky to be blue, when in fact you can just look outside and see that the sky is blue, that looks goofy, right? I should use the divergence test if I can use the divergence test. The other reason is totally fine. Right, okay, I'm way afield from what I'm trying to talk about. That series diverges. So I kind of think this series diverges. I'd like to be doing a comparison test of this with this. It's worth thinking about. The limit comparison test needs me to take a limit. The direct comparison test only needs me to say why a thing is bigger than thing. That means usually the direct comparison test is simpler. It's going to involve less writing. I'm less likely to make a mistake, like there's no limit to write out. The writing is also nicer. If I look at what I had to do here, I've got all this computing a limit going on. It's kind of ugly. I'd rather do this just with sentences if I can. Like I was able to do when I did the prior example. This is all sentences. It's better writing. So what? Can I use the direct comparison test here? This thing diverges, and I understand the direct comparison test. I want to show that if I think the thing diverges, I need to show that it's bigger than something that diverges, right? Being smaller than infinity doesn't tell me anything. Being bigger than infinity is the one that tells me you must be infinite. Smaller than infinity could be infinite or finite. That corresponds with bigger than finite could be infinite or finite. Smaller than finite is the thing that you learn something. Is this true? Have I made the fraction bigger? Why would it be true? I guess the thing I want to compare it with is maybe 2n squared over n to the square root of n cubed. Is this less than that? You made the top of the fraction bigger. Oh, but you made the bottom of the fraction smaller, so you don't learn anything. If the top was bigger and... Wait. Yeah. If the top... I said that wrong. The top of the fraction is bigger, that's good. The bottom of the fraction is bigger, you added something on inside the square root or outside the square root. You're making it bigger. Making the bottom of a fraction bigger doesn't make the fraction bigger. So I can't conclude immediately that this is bigger than that. If I was really, really dead set... Okay, so because it's not obviously true, direct comparison is not the easiest path to go down. There are ways to force it down, and I'll do one of those in a second, but the easier thing to do here is probably limit comparison. This being this probably tells me that the limit equals that. This time I'm gonna incorporate my scratch work into the problem. I'm gonna say this was all my scratch work. I'm gonna start writing the solution by doing the limit. And this is just gonna be a big display that doesn't have a sentence attached to it. The limit, as n goes to infinity, of... I want to put the known one on bottom. I'll put n to the 1/2 on bottom. I'll put 2n squared plus, no, the top is a big fraction, 2n squared plus 3n over the square root of 5 plus n cubed. What is this limit? Okay. I didn't do this limit up here, but I think this is the right thing to take the limit on. This is the other nice thing about writing this right now, is if this is wrong, I can go to put a big X over it and try again on the next line. And if it comes out gross, I can always say, well, this was scratch paper too, and then incorporate the shorthand version of it into a paragraph. But this ratio is already so gross that I will feel gross putting this into any paragraph anyway. The thing is too ugly to put into a sentence. I'm gonna do it outside as a display. What is this? This is the limit of n goes to infinity of, we're adding an extra n to the 1/2 on bottom. And on top we have 2n squared plus 3n. The standard trick is multiply the top and bottom by the 1 over the biggest thing on bottom. If I had p squared minus 2p plus 1 over 3p to the 8 minus 7p to the 4th plus 2p minus 6. The thing you would multiply the top and bottom by is 1 over p to the 8. This will be a constant, and everything else in sight will go to 0, so you'll have 0 over a constant goes to 0. You want to end up with a constant on bottom so that your fraction is either constant over constant or 0 over constant. Preferably constant over constant. Preferably... Sorry, I need to pause 1 second. My other class is taking an exam, and a student's got a question, and I should answer a question about an exam immediately. I'll be back in 1 second. I'm back. Sorry about that. Oh. What were we doing? We're taking this limit. I'm dividing that by n to the 1/2. Yeah, the standard thing you do is you multiply the top and bottom by 1 over what is the biggest part of the bottom. But the real key of that bottom is what is like the essential size of the bottom. The bottom is about square root of n cubed. That's the square root of n to the 4th. That's n squared. I want to multiply the top and bottom by 1 over n squared. Because n squared is n to the 1/2. I guess I'll write that here, n to the 1/2, n to the 3/2. When the n squared hits everything on top, it'll hit that and become 2. It'll hit the second one and become 3 over n. On bottom, the 1 over n to the 1/2 cancels with that. The square root of n cubed becomes the square root of each of these is being divided by n cubed. So I get 5 over n cubed plus 1. This limit is 2 plus 0 over the square root of 0 plus 1 is 2. We did the limit successfully. It's better to do this stuff in a paragraph than out on its own. I think I already spent enough time saying this thing is too gross to put inside a paragraph, so it's probably cleaner to leave this out separately. But now I want to make my paragraph below this referencing the gross stuff above. Since we have that n to the 1/2 and 2n squared plus 3n over square root 5 plus n cubed are positive. I guess I should examine the parts of this sentence even. Why am I saying that? Because now the first word of my sentence is something mathy, and I can't start my sentence with a capital letter. And, so we can use the limit comparison. With the above limit, that sounds goofy. So we can use limit comparison by the above limit, by the above computation. Since the sum of square root of n diverges, I can't start my sentence with the sum of square root n. I'll reword it. Since the sum of the square root n diverges, we have the sum, the other sum, the given sum. This is gross to write out. Diverges also. That's it. You might emphasize, so here's the place where it kind of matters what counts as the limit comparison test. For classes where this is a version of the limit comparison test, like this paragraph is totally perfect, if all of this also counts as the limit comparison test, then I kind of want to clarify the limit comparison test wouldn't work for us if the limit is it 0? If the limit was 0, then the top would be smaller than the bottom. We wouldn't learn anything from being negative infinity. So you have to say, we can use the limit comparison test by the above computation. Like, add in something like since the limit is 2 is not 0. Since the limit is 2 and 2 is greater than 0. I think you don't really need to add that part. This is the thing that's like the formal box around it, limit comparison test. You're welcome to use the other facts also, but I'm going to say that I don't want to say they're not the limit comparison test, because when you use this fact, you want to say by the limit comparison test and what you're talking about. Yeah, but because it's sort of, this is one of the limit comparison test works. I'm just going to say I don't need to greater than 0. I can see there being a case for that paragraph being there. I think I'm not putting it there. So here's our answer. We're doing some stuff that's not in paragraph form here, which you're allowed to do, but you should have a paragraph in what's going on, and that paragraph should be connected to, should incorporate whatever displays you're using. Okay. So there's an example using the limit comparison test. How did we do it? We understood the size of the thing. That's basically it for positive series. Let me pull out the homework. Actually, let me go back up to, let's fill in what the direct comparison test. If